Okay, so the second talk will be by Professor Siebert from University of Hamburg. He's going to talk about geometric quantization of semi-positive varieties inspired by symmetry.
Yeah, thank you. It's a great pleasure to be at this privileged place of the world. I mean, this view I could have every day, but only very few people can have it. So for everybody else, it's nice to visit. And I apologize for a slightly long title. When I got the invitation to the conference, I was happy that gets the occasion to talk to a slightly different crowd, because there are things in the back of my head already for a couple of years where I think that that what I'm doing with Mark Rose fits into some kind of much bigger picture and has some implications to many other things that are somewhere in the air in the interaction between physics and mathematics around quantization and moduli spaces, invariance, quantum invariance, and so on. Okay, so by and large, I want to start where Professor Anderson stopped, essentially. Okay, so that doesn't mean you have to remember everything he said, but so let me start with some overview. So let's give some overview. It's late in the day and everybody's tired. My plan is not to cover too much. I can stop any time here. So we'll just go slowly, and if you get lost, please ask. So that picture was already on the blackboard. So there is this SYZ mirror symmetry picture that we now know is kind of too naive. We know for many years that it is kind of too naive. But as a first approximation, that's how mirror symmetry can be viewed on. So you have some B, and then there's an X and an X check. So this kind of this mirror pair. Now these are, you could think of Calabi Yau. There are many other classes of varieties that are hidden in this semi-positive thing here, even non-compact. But let's stick to the Calabi Yau case. So let's say these are Calabi Yau n-folds. Maybe think of your favorite Calabi Yau 3-fold. This is complex dimension n, so maybe I should write 2n, and that would be a real n manifold. So let's, for example, think of an S3 if you have a Calabi Yau 3-fold. And then these are torus vibrations, and the tori that you get, so this comes with actually an affine structure. So this is an affine manifold, and it comes about, so real affine, yeah, so integral affine, coordinate transformations in GLNZ, semi-direct for Z, and then this thing here, there's some good subset. I mean, it has singularities, yeah, with singularities in codimension 2. So let's denote the complement of this singular set B0, and then in here you have a T star B, that's a cotangent bundle, naturally it's a symplectic manifold. And you divide out, so here I differ with Professor Anderson's talk. I use a star here. That's the integral differential forms on. Okay, so I should have B0. While on this side you have a TB0 mod lambda. Now this is naturally a symplectic manifold. This naturally is a complex manifold, but both structures are kind of a little off. And this structure is more off than this one, because this still can honestly be embedded into the thing as a symplectic manifold, while this can't be honestly embedded. It's a too naive picture. Okay, but we already saw that this X check that has some canonical. Well, now this almost doesn't make sense, but think of these as really being honest Calabi Yaus. Has a canonical up to Hamiltonian isotopy. Has a canonical Lagrangian. Has canonical Lagrangian sections, and they're essentially given by the graphs of the evolution. So there's a tangent space. You can look at the rays emanating from a point. at the speed proportional to the distance. And the graph of these give Lagrangian sections. And we saw this picture where you wrap around these tori. You know? So these are these sections, let's call them LD. And D is the slope, so this would be slope 0 or L0, that's the speed. Sorry, that's X check, exactly. And then, and you observe that the integral point, the intersection points, so the L0 intersected LD, are naturally the 1 over D integral points of B. Simply because you wrap around, you divide out the integral lattice, so you wrap around once if these points have integral distance, well, an integer, yeah? Or 1 over D, if you go by speed D. And on X, that is naturally a symplectic manifold. You have these, the 1 over D integral points have an implication in terms of horizontal fibers. So that means, we'll define it later on again, so this side comes with a line bundle L. So this first term class of L with some connection is our symplectic form omega. And then we want this to be L to D.
So this line bundle on what? I'm a little lost.
Sorry, say again?
L is a line bundle on whom?
On X.
On X. Okay.
On X. So L is on X, and here would be 1, here would be 0, 1, and I'll check, which we won't need. That's perfectly symmetric. So L, it's just the one which has, it's a U1 bundle coming from the symplectic form. So there's this line bundle, and then you can restrict it to the fibers. So if I take a B in here, 1 over D integral point, you can look at when this, that's a flat line bundle, that's flat, and you can look at when this is trivial. And that characterizes these 1 over D integral points. These are called Bohr-Sommerfeld fibers. So the pi over 1 over D are these Bohr-Sommerfeld fibers. That's a special meaning in geometric quantization. And then homological mirror symmetry, and that's a story we know for a long time, suggests that that these intersection points, these are homomorphisms given as homomorphisms, as morphisms in the Foucault category, they should be canonically identified with elements of this well, with sections of X of L to D of X, holomorphic sections. Okay. So then with Mark Rose, well, the good news is we have such sections. Okay, we have sections. What we don't have is this whole story. So let me review what this is. So the less naive picture gave with Mark, and rather than thinking of this as a static picture for 1x, we look at this as we give a degeneration picture. So we construct degenerations, a class of degenerations, so that we denote the total space by some curly x, and that sits over some base. In reality, it's really just a speck of some complete local ring. Yeah, but think of this in some situations. You can easily get this into an honest, let's say, a disk or something, maybe some small analytic domain, and that is the central fiber x0, and the x0 is a kind of very dramatic degeneration. The x0 splits your X into kind of linearized pieces. Everything is to be understood with a grain of salt, so my linearized pieces are just toric varieties. So there are certain polytopes, integral polytopes, so the sigma are Z polytopes. And the P sigma is the toric variety with momentum polytope sigma. Okay, and that's x0, and it has a kind of degenerate momentum map to the union of sigma, and that will be my B. So let's call it mu sigma. So the momentum polytope would map mu sigma, would map p sigma to sigma, right? That's my momentum map. So there is a kind of, we get a kind of linearized picture of this, where this correspondence actually holds on the nose. But then we start deforming, and this process to go from x0, the central fiber, to x is complicated, but it's canonical. I mean, there are a couple of parameters involved. Don't want to waste time in explaining all the details. But this is a very canonical process. But it holds, I mean, the kind of symplectic geometry that goes in is kind of silly. The only thing is you need something like a degree to tell when you converge. Other than that, the construction is independent of this, although we work on this side. Okay. So some more features of this construction. So one thing that explains the semi-positive in my title is so that we can do this in a rather large class, not just Calabi Yaus, but we will always get that the fiber for T0, assuming that this actually makes sense, but it makes sense as a generic fiber, the minus kx is effective. So an effective divisor. So like PN, Fanus, and stuff like this, or Calabi Yaus, certainly abelian varieties fit into this class, and some affine varieties and so on.
And are you getting this way a basis for H0 of the fibers?
That's what I'm going to explain, yes. That's exactly the cool thing. We have a canonical basis of H0 of this line. So, so this is canonical. So this whole thing is canonical. The construction, construction is canonical up to some obvious non-uniqueness. And the construction works via what is called wall structures. Also appear in work of Constellations Obermann. Wall structures on B, which is this, well, the walls are really straight in the affine structure that I've written down. This affine structure that I have.
How do you normalize holomorphic sections?
I don't know it. I don't.
Oh.
This is the ambiguity I have.
Oh.
I'll get to that.
So it's
Well, ours are normalized, you will see, that because we know that you will see. If you still have the question at the end of the talk, please ask again.
thank you.
Should be obvious. So let me do an example. So something that really fits into this class and that we will get out of our construction is a degeneration of a quintic. If I want to make these strong claims, I should be more precise here. Don't want to lie too much to you. So let's take this log family. Let's say P4 cross, let's say A1, where the T is a parameter. By the way, this T parameter, well, that's not our T. Don't need to measure this anymore. Okay, so this is a degeneration of the quintic. It's a Calabi Yau, famous Calabi Yau threefold. Okay, and then let me get to these functions. That was already being asked. Let's go work with Paul Heckman and Sean Peel. Did I give some? Yes. So shortly, even in the year where we were about to finish this, we were discussing about the fact that our construction comes not only with the deformation, unless in a certain cohomological obstruction vanishes, okay? But once it vanishes, the whole thing comes with a polarized line bundle, polarizing line bundle. So the whole thing has a line bundle on it, And we have a canonical basis of sections. So this X comes with L, relatively ample, and, oh, this is maybe, let's say 0.8 or so. It was probably already finished in 0.7. Yeah. The basic idea is already there in 0.7. With L and a canonical basis of sections, theta m, and the n run over d into the points of this Fi manifold that you took as your base, just as you would expect from the naive homological Merson. Okay, and then I hope Professor Xavier will project to the use of the term theta function here. These are generalized theta functions. Why? Well, we can apply our construction to the case of abelian varieties. So if xt are abelian varieties, then we really retrieve the classical theta functions. And this picture that Professor Anderson drew in this talk about the elliptic curve and this curve counting and so on was actually written down by Mark, if you want to see some details for this, in the clay book. There's a clay book, Dirac clay brains and mirror symmetry or something like this. And it's worked out there in full detail. Okay, but that was just the elliptic curve, and but we have this now for everything. And if it's a toric variety, well, that also exists. There are non-trivial degenerations of toric varieties. Then actually outside the central fiber, everything is just a product, but the central fiber might still split. Yeah, that's what Alexeyev calls, what does he call this? Broken toric varieties. Yeah, so if xt are toric varieties, well then, of course, the theta m are just monomial. These are the usual monomial sections that you have in toric geometry of some toric line motion. Okay, so then of course, okay, you have these things, and well, maybe to answer the question here about the normalization, maybe I can do this right here. The point is simply, if you restrict to your central fiber x0, the theta m become monomial sections. So our central fiber x0, remember, x0 was a union of toric varieties, p sigma. So then I have this L restricted to p sigma, and these have monomial sections. So if I restrict it, then this is also monomial, and that of course gives you a distinguished normalization. I'm not sure if this is a natural normalization. Okay, intrinsically, that's a whole. What my talk is all about. We don't know what these functions are intrinsically. We only know what they are in our construction. But the question is, of course, once you have some canonical construction, you wonder, okay, what does it mean? What does it buy us? Yeah, rather than just being a beautiful set of functions.
Because it's monomial with respect to some particular preferred coordinates, right?
Yeah, I mean, it's just on the central fibers. Then you turn on your deformation and all hell breaks loose. And usually I cannot even write them down explicitly. I mean, I cannot write down all families. It's a very complicated process. Say you want to do it for a K3 surface or something, nobody can do that. Only with hindsight I can say, okay, these are functions that have these and these properties. And for example, oh, here, maybe that is a non-trivial example. The zi in this case are actually theta functions. The zi are certain thetas for the vertices of the polynomial composition. So B is a simplex, is a three simplex, and these are the vertices. But that's a coincidence here.
No, I just meant the automorphism group of these central fiber.
Yeah.
That they mix up monomials.
Yes.
Yeah, so
Yes.
if I change by some homomorphism there, I will get a new basis, right? Which is not the same as the one you started with.
Yes, you have I mean, the action has some weights, and of course it does something.
So there's a choice on the central file to get the basis.
Okay, depends how. Okay, depends how what a toric variety is for you. I mean, there is certainly, once you have a sigma, there is a toric variety and there is a distinguished basis.
Yeah, when you have the action fixed.
Yes. Okay, so question. Apart from the interpretation by homological mirror symmetry, but that's just an inspiration that we want to prove. It cannot be used really to define things. So what is the meaning of these theta m? And then there's this dream I'm having already for quite some years. Our construction makes mirror symmetry very nice on the complex geometry side. Everything is in a certain class of things. Everything seems to be canonical. The Kähler metric side, the Kähler geometry side, the best we can still do is say, okay, we have a Kähler class, and then we apply Yau's theorem. And that's unique, but it's not really explicit. It has a much less explicit kind of feel to it than what we do in the complex geometry side. And once you have these sections theta m, you could talk about the Bergman metrics, which are essentially pulled back Fubini-Studi metrics, but then you let your d go to infinity. And there are all kinds of approximation theorems, starting with Tian and Zeldich and so on, that tell you that you can approximate. So the question is there some way where we can explicitly use the theta m's with a given normalization? Now comes the normalization issue. Or with some other preferred normalization that produces the Ricci-flat metric asymptotically. So can you kind of approximate the Ricci-flat geometry from the Bergman metrics? I mean, what is hopeful is our family or degenerations come with a big automorphism group, and the theta functions have different weights for the action. So just by abstract reasoning, they are orthogonal for the Ricci-flat metric. And that's one of the conditions you often use in proving these things. But okay, this is just a dream. Okay, I mean, when one knows such things work for the abelian varieties, certainly also for toric varieties, that's boring. But there's no Ricci-flat metric there. So, but in the Calabi Yau situation, nothing is known. All of this has been already hinted at by Tyurin I, who unfortunately died in 2002, who early on advertised the view that homological mirror symmetry should have something to do with geometric quantization. There's a whole series of papers about this, and I took the occasion of preparing for this conference to finally really read these papers and dig out which ones are really the relevant ones, because there's a whole, here's like, I don't know, maybe 8 papers or so that all look very similar. So what you should do if you want to see what was known already before we started even our program, it was started in 2002 maybe, 2001, 2002. Here's the notion of Poisson basis. So the relevant papers are, for this are Gorodensev, Tyurin, abelian Lagrangian algebraic geometry, algebraic So that was, what was it, 2000. That's a public version in SXTL. And then a Tyurin on Bohr-Sommerfeld basis. And all this is based on a paper, slightly different focus by Borthwick, Paul, and Rudiger, which is, that was the other one. And that's 95. About geometric quantization and some pseudo-convex domains. So let me explain what this is. I mean, it was a little bit already hinted on in the talk by Professor Anderson. So you start with this symplectic manifold, and you get this line bundle, the U1 bundle, we call it L nabla. So such as C1, this is omega. And then you have these Bohr-Sommerfeld files, right? Just as before. So you can look at L nabla restricted to a Lagrangian, and then this Lagrangian is called Bohr-Sommerfeld. This is trivial. So this is not. Oops, is that mine now? So I want to emphasize that this is not restricted to the case where the Lagrangians arise as fibers. So since there's an infinite dimensional space of Lagrangians, of course, you could take your Lagrangian fiber and look at the deformation as a Lagrangian, just given by closed differential forms by the Dabou-Weinstein theorem. And in there's a codimension, a finite codimension submanifold consisting of Bohr-Sommerfeld Lagrangians. Yeah, sorry, this is. Oh, maybe I shouldn't use L for the. I want to use S for Lagrangians actually. Okay. So yeah, so the example. That's what I was already using. I said if M is a Toy variety, and you look at the moment map, this moment map mu M to sigma. So this sits in Rn, and that identifies the M with T star sigma mod lambda star, and a compactification of it. Then we have, of course, the omega is the alpha, and alpha is the equilibrium. So some PIEQ out. And here you can almost see how you get this integrality for the Bohr-Sommerfeld points. So you have that S is mu inverse P is Bohr-Sommerfeld. You can only have this P is integral. Now the P are the coordinates on sigma, right? It's the actual coordinates. Okay, and then we have this fact that if you have a codimension, so if you look at the normalized space of Lagrangians, then in there's another moduli space of Bohr-Sommerfeld Lagrangians, and the tangent space, of course, this has tangent space at S. Oh, I need more space. So the tangent space here is a closed form, so Z1 D1 of S, and then in there you have these Bohr-Sommerfeld Lagrangians. Well, this is given by these closed forms, so by the forms that by the exact forms. So this, of course, has codimension. So this is whoops, that is the one you're wrong. That's the TSBS. Yeah, so this has codimension. So it has codimension equal to H1 of S. So if you have a Lagrangian torus fibration, the torus, like in the SYZ picture, right, that explains why the moduli space of Bohr-Sommerfeld Lagrangians has codimension n, just the dimension of the base, and hence, if your deformation is general, these Bohr-Sommerfeld Lagrangians are discrete in the base. And this certainly is the expectation that we have for special Lagrangian fibrations. Yeah, so here we want to take this S to be a special Lagrangian in special Lagrangian fiber, torus fiber in X, assuming such exist. So then the conjecture is, for the whole picture to work, we have now two things, right? So we have our center fiber and we have Bohr-Sommerfeld fibers for the center fiber. That's just for the silly toric structure that would, let's say, we decompose an elliptic curve to a union of P1s. That would just be the positive curvature kind of scalar structure on P1. That gives the ones which has the right number of integral points by mirror symmetry. Right? This is the one how we constructed our center fiber. And then we go off, turn on T non-zero, we have some smooth Calabi Yau, and hopefully, away from some bad set, we still have a special Lagrangian fibration. Or we have a special Lagrangian fibration. And there we have Bohr-Sommerfeld fibers that we, by this argument, should be discrete. Okay? Now, if the picture is to work, especially the numbers are to match, we need, or the picture suggests that the Bohr-Sommerfeld special Lagrangian fibers should converge to the Bohr-Sommerfeld fibers of the center fiber. So that would be a conjecture. So we have the Bohr-Sommerfeld fibers of, let's call it S0, yeah, of this X0 over B. Well, don't take this too literally, right? So we have some singular locus here. Let's just assume, for the time being, and that's not a headache, I can comment on later on, that these Bohr-Sommerfeld fibers are really in the interior of your not at the toric boundary, and that doesn't matter at all. Yeah, so we would be at a situation where I'm having a Bohr-Sommerfeld fiber here, and I'm trying to deform it away from the critical locus of the projection to the base. That is a projection. Oh, that was also a pi. No, that was a mu. I see. So that's a pi to S. Yeah. Oh, was this S2? That's bad. My parameter space disk. Okay. Okay. So the conjecture is that these Bohr-Sommerfeld fibers of S0 so that's the union of P sigma, deform uniquely to Bohr-Sommerfeld fibers of special Lagrangian fibration of XT.
Question about that. Could one imagine that there are several Bohr-Sommerfeld fibers that converge on one and the same singular fiber over the special fiber?
Well, my B on the special fiber suggests that doesn't happen. Yeah, so on my B is really as nicely as you could think. It's just the union of momentum polytopes. This is just subset of Rn with its given integral structure. So there these points are nicely spaced away from each other. So that fear actually does not happen. Maybe when that would probably what one thinking of symmetric geometry. I will comment on this. But apparently symplectic
singular fibers, I mean singular Bohr-Sommerfeld fibers, I think is
that might be the case, but remember our deformations are kind of nice. So there are certainly situations where you could force this behavior. For example, yeah, I could even build one. I could use some K3 families that we know, and then I contract all components but one.
Yes.
And then, of course, all the stuff will go there. Yes. But, yeah, so that's apparently, I mean, our setup is exactly so it would work. And it shouldn't come together because our counts are right. We have as many integral points as the dimension of the spaces, of the section spaces, holomorphic section spaces give you. And that's exactly the number of Bohr-Sommerfeld O's. So if several come together, we have a problem.
So from physics here, we expect that special Lagrangians, as you start defining the base transform, that they can appear and disappear. So that there's
No, that's different things. These are Lagrangian spheres. These are that's different. These give these like conifold transitions and so on. That's different. This is not the behavior we have here.
So that's a distinguished set of special Lagrangians.
It's a different set. These are special Lagrangian tori. These are tori. Any special Lagrangians is in a vibration that must be torus.
And
because
it's sensible to ask about their number. So how many of these are?
That's a vibration. That's a continuum. I mean, you sweep out your whole S.
Okay, yeah.
So each point generically is exactly one. It's a bit off, but yeah, essentially. It's only true limiting the option. Okay, so what else did I want to say? Yeah, so if so, let's assume that this conjecture is true. And I'll comment on why this is something serious has to be proved. And this is maybe even goes against established kind of pictures from geometric analysis. Okay, if so, we obtain, and that's now, well, you could actually, that unique deformation might not be so hard actually. No, I wouldn't say this. No, what I want to say is, once you are off from your central fiber, the unique deformation shouldn't be hard. What you're saying is that a Bohr-Sommerfeld, an isolated Bohr-Sommerfeld Lagrangian, deforms uniquely as a Bohr-Sommerfeld Lagrangian if you deform your symplectic structure or whatever, symplectic form. And that should be just an implicit function theorem. Because you have full control of these moduli spaces. But what is hard is to go away from X0. So if so, we obtain the following. We can do something like an integration. So we have this flat section on my Bohr-Sommerfeld torus, flat section of the line bundle L, and I can compare my holomorphic functions with this to this section. So each holomorphic function is a multiple of this section, this flat section. So let's write. So if I have an element in LT, so let's call this little s maybe, or too many s here, huh? That's a capital S, it's a little s. Then I can restrict this to the Bohr-Sommerfeld fiber. That's a capital S now. Oh, that should be an ST. No, S is fine. I want to restrict it to ST. And then write it as a function times sigma. And sigma is a flat section. That's not the sigma I had before. That's a flat section, yeah? So then I get a map to C by integrating. So I map the S to the integral over the fiber, that was my ST, of something like S over sigma, so to speak. That's the F, right? And then d mu, and the mu would be, d mu would be an invariant, a constant matter, yeah? On the fiber. And that makes sense, and now it comes into play that we actually have a vibration. We need a vibration for that. It's not enough to just deform the Bohr-Sommerfeld, we need a vibration. So that makes sense because we have a vibration.
It's basically inherited from the affine structure of the base.
Exactly. Yeah, but you need this, if you just have one Lagrangian, you don't know. So in this whole, if you look at these papers that I wrote down, there are these half weights coming in, everything depends on a choice of half weight. This disappears up to a constant in the setup that we are looking at, the vibration setup.
But the measure just induced by dependent matrix, right?
Sorry, say it again?
The measure induced by dependent matrix, right?
I don't need that. I don't need that. There's no Riemannian geometry. At this point, there's no Riemannian geometry.
Okay, so how I can track this?
Well, the cotangent, the tangent bundle of ST, the cotangent bundle of ST, right? At a point of, let's say, what, x, that is canonically identified with the tangent bundle at the space of the point mu of b. Just because we have a momentum map. Just symplectic geometry. And that's why I can talk about constant measures. And then this is defined up to a constant, yeah? Up to one constant number, okay? So what this is saying is, so the upshot is, of this discussion is, that each Bohr-Sommerfeld fiber, up to the conjecture, each Bohr-Sommerfeld, or each 1 over d into the point, or each into the point in this situation, so each Bohr-Sommerfeld S provides a distinguished line in the dual space. Or maybe I should write it like this, yeah? Oh no, they're not C, that's better. T, dual. Okay. So the question then is, are our theta functions just the dual basis of this? For Bohr-Sommerfeld Lagrangian fibers. And that would be an intrinsic characterization of our theta functions. So let's see, I have like, what, 5 minutes, 7 minutes, 8 minutes left?
8 minutes. 8 minutes.
Thanks.
Maybe I can comment on this because in my case, where I have the hitching connection that singles out the theta functions for me, the non-abelian theta functions, the answer to this question is no.
Which question is no? That they are not.
The question you just wrote on the black one.
This, oh,
That one.
is that true? Oh, I understand.
They are not covariant constant with respect to the hitching connection, this construction.
Okay.
They
Oh,
are
I haven't
simply
used this.
classically as the level of the theory goes to infinity,
Aha.
but not a finite k.
Okay, I see. So I see. So somehow I read from Tyurin's papers that this should be true.
Yeah,
Is there something off?
Yeah, that's not right.
He made a mistake or something?
Well, he thought a lot about this sort of semi-classical picture of this, and semi-classically this is correct, but not in Schoenstein theory for finite k.
Okay. So I'm curious to learn about this. What goes wrong there? But anyway, this is a different case. Must still be right. You know,
You
so
see, it's essentially the following thing. You just take the distributional section, and then you just project orthogony onto holomorphic things. That's almost equivalent to what you're doing. And so you just, the topics, if you look at this 3-author paper you wrote about earlier, they actually show that the Turkish projection is regular enough to hit such a distributional section and get a section, so to get a dual construction to what you're just saying now in the H0L.
I'm not claiming that the restriction would be sigma or something like this, right? That's not what I'm claiming.
No. But all I'm saying is just that these are not covariant constant with respect to the hitching connection.
Okay. Anyway, so let's so that's interesting.
It's a general thing that the Turkish projections are only semi-classically.
But it is true for abelian varieties.
Yes, but that's because semi-classical. I mean, that's because the Turkish projections are.
I see. Okay, let me highlight some aspects of this. So let me just give two aspects. So the first is so it's a convergence. So maybe you might think, okay, so let's just take our Ricci flat matrix and take the limit, and then everything is nice. But that's totally off, apparently. So the convergence of the Ricci flat matrix gives a very different picture. So this has been studied by many people, including Jul1. Is not understood here. In this context. So let's just look at a very simple situation that everybody can do at home. It's a little exercise. So if you look at what's happening to elliptic curves, the fiber xt up to a change of coordinates that can be just written as c star mod something like t, c star mod t. So this would have a fundamental domain that is an endless 1 t, and then you do by the transaction, it gives a nice torus. That gives you the degeneration of complex structures. And then the x0 could be, for example, something like a union of 3 p1s. Now what's happening metrically, and you can see this when you do the computation, the area blows up in this. If you take the usual flat thing, the dz, dz bar, the area will blow up. And then if you rescale, and even worse, the area gets concentrated at these points, at the singular points. And also the diameter, the distance gets concentrated. So metrically, in the limit, everything you see here, the interesting part, gets collapsed to a point. And what seems boring, it gets blown up to a big thing. So you really get the kind of dual picture. You get the dual graph. So metrically, the Gromov-Hausdorff convergence gives exactly the other kind of thing. You get a circle, but these components here, these components, what do we call them? Maybe p sigma I. They go to these to actually point, and this whole thing is a circle, but with these things contracted to a point. So that's totally off. And once apparently, that might still be true that the Bohr-Sommerfeld fibers converge correctly, right? That might still be true because that has nothing to do with metric geometry. That's just symplectic geometry. You mustn't forget that there's also something interesting happening to the complex structure near these points. So they're both degenerate, and in the end, everything could be fine. But so a discussion is going and embarrassingly, even this situation hasn't been worked out. I think we have to the other thing is, which is maybe interesting, is that we have in our local construction, we have local charts. So not abstractly, but the way we do our construction, we get this x, 0 and x, and the x is really constructed to finite order. So we do this whole thing to a finite order, which of course is like doing topology or something. But in finite order, we explicitly have charts where, namely the charts, well, it's all glued up from D. Yeah? So you have your D, and then you have these integral points, or 1 over D integral points, and there's a certain wall structure here. And then each complement of these walls has a chart. Actually, any point is a chart. But anyway, so if these charts, they give us charts for x. And in these charts, the holomorphic n form, so this is h0 x omega n. This just has the standard form, dz1 is the logarithmic model form. Okay, so this looks like the c star to n kind of thing. Finish very soon. But the omega seems to go off. Yeah, so the vibration gets messed up. Yeah, so the torus vibration, and this is preserved by the wall structure, preserved by wall crossing. So you will have other charts at other points, like here, and then there's a wall crossing. That would be one of these walls. So that would be a wall crossing. And going from one chart to another, you have a wall crossing, but this preserves the holomorphic n form. But the torus vibration is not preserved by wall crossing, as you would expect, right? So even here we see something is going on in symplectic geometry. Okay, so to say anything more, I would probably have to tell you some details of our construction, but I don't have time. And feel free to ask me later on. Thanks for your attention. Any questions?
Can the theta function control the type of singularities of the singular special complex vibration of the mirror?
Of the mirror?
Yeah.
Types, in a way. So, I mean, you know very well that the theta function have to do with holomorphic disks in the mirror. And the holomorphic disks, they have boundary on Lagrangian fibers, and they end on your singular set.
Yes.
In this way, they do, but explicitly.
Because I think the only type of singularity we sort of understand is the conical singularity due to Dominic Joyce. I wonder if there are other possibilities which can be maybe indirectly understood from the
I mean, we have good control of our singularities. I mean, we have local models of our singularities, so I could tell you what the singularities are in our family, not of the torus vibration, not of the special Lagrangian vibration. I mean, I don't know. Yeah, there's that's subtle. It's something we cannot directly read about. It is there, hidden in some way, but I don't know. Any other questions?
So the coordinate function in the quintic case, you said it is a theta function. You said it could be
up to scale. It's a silly argument. You just have this big automorphism group, discrete automorphism group, and then you look how it acts on your section space.
So do you construct it from a Lagrangian section? The theta function is constructed from counting disks somehow.
Sorry, say it again.
Theta function is constructed from counting disks.
No, it's not constructed from counting disks. It's constructed from well, it should have an interpretation in terms of counting disks. That's true, but it's not constructed this way. It's constructed by doing the inductive construction of the wall structure and then writing it down. Okay, we just write it down essentially. We write down a function that is preserved by this wall crossing, like we can do. And then what was your question again? You wanted to know
for the quintic,
well, for the quintic, the argument is simply we have functions that are invariant under the discrete symmetry group of this family. So you write down a family which has a discrete symmetry. Yeah, and then you know, okay, we have these functions and they obey the same symmetry, and then there are just not so many. So up to scale, these are theta functions. And you can check the normalization on the central fiber.
So how about for K3 and
in general, they are difficult. I mean, they're of course, for each fixed T, they're algebraic, because it's just sections of an ample line bundle, but the variation in T could in principle be transcendental. And they have to be. I mean, the way we write it down, our deformation parameters are these canonical coordinates, solutions of Dicker-Fuchs equations, if you compare it to actually algebraic coordinates. So they have to be, in the way they are written down, they will be transcendental. The question then is there maybe some non-algebraic coordinate change that turns them into some easy functions that sometimes can be made. So Mark in his work with Paul and Sean on surfaces, he has certain cases where they can explicitly write down these theta functions and they just see, okay, they are algebraic functions.
Did you try to compute the connection for which these are covariant?
That was the question I wanted to discuss with you. I think that is one of the, right. So there are two possibilities now. So either forget about the whole X0 story and just say, okay, we have a special Lagrangian vibration. Hopefully someday some nice person will prove that they exist. And then see what the connection is. Right? Because, so, which makes these functions flat. That should be a doable task. I think that can be done. And the other thing is we have to understand this, somehow make sense of this degeneration in some way that preserves the boson-Morfeld fibers, and then show that our theta functions are actually these flat sections for this stuff. And I'm really curious how our wall crossings interact with the Ricci-flat geometry. It seems to be some really interesting story behind. We don't know.
We don't have any questions. Let's thank the speaker.